This video is part of the MCAT chemistry video course. Subscribe and hit the bell if you'd like notifications about new videos, and visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we're going over Le Chatelier's principle and looking at disruptions to equilibrium and then applying that to gases and heat as well. In the last video, we established what the reaction quotient, or Q, is and what the equilibrium constant, or KEQ, is. And we established that anytime Q and KEQ were not equal, the reaction is going to proceed in the direction that makes them equal. So you should be okay with determining what direction the reaction is going to proceed if you have Q and KEQ. Now what we want to work on is predicting what direction the reaction is going to proceed whenever a question just tells you that a reaction is in equilibrium and then it gives you some disruption to that equilibrium. You need to be able to figure out what direction is the reaction going to go. And Le Chatelier's principle tells us that the reaction will proceed in whatever direction restores equilibrium. So after equilibrium is disrupted, the reaction will try to restore equilibrium. So the way that they usually have you approach these types of problems, they'll give you a reaction like what we have here. They're going to tell you that it's in equilibrium, and then they're going to present to you some disruption. And then you got to figure out what direction is this reaction going to go to offset that disruption and restore equilibrium. So let's practice that here with our equation. We'll say that this equation here is at equilibrium. So remember the KEQ, that value does not change. It is a constant that is specific to whatever reaction you're dealing with. The only thing that changes KEQ is temperature, and we're just going to say we're operating at a constant temperature here. So currently, the ratio, or this fraction, whenever we plug in the concentration for those three things, when it's at equilibrium, that's going to equal the KEQ. And now we'll introduce some disruption, and then we'll predict what direction the reaction is going to go. So our disruption that we'll do right now is lowering the amount of N2. So if we lower the amount of N2, the way you want to think about this is that the N2 in that equation now goes down. So previously we were equal to KEQ, but now that the N2 has gone down, our fraction is larger than KEQ. Because the value of the bottom part of your fraction has now gone down. So now we need to get the value of our fraction back down to where it was before. And the only way that we can do that is to decrease the amount of NH3 or increase the amount of H2 and the amount of N2. So you just want to think about what direction is the reaction going to go to accomplish those things. And hopefully you can see pretty easily that the reaction would proceed to the left in order to accomplish those things. And it's going to do that until the concentrations, when plugged back into this equation, would give you the KEQ. The second that happens, the reaction will now be back in equilibrium, and then the forward and reverse rates will be equal again, which would make those concentrations then constant once it reaches equilibrium again. That would be a pretty straightforward question that they'd give you. Sometimes they will make the disruptions to the equilibrium a little bit more tricky. So for example, they might say that we do something like add HCl to the solution, which HCl is a strong acid, and we'll go over that way more in an acid-base video. So whenever you add HCl to a solution, what you're basically doing is just adding hydrogen. So maybe they even say we lower the pH of the solution, and then ask you what happens to the equilibrium. So if the hydrogen ion concentration increases, then you need to think about, does hydrogen react with anything in this equation? And again, you'll be way better at this after you go over acid bases, but hydrogen would react with NH3. So we do hydrogen plus NH3, which gives you NH4 plus. So after you have figured out how this change affects your reaction, you just need to think about, do any of these concentrations change? And hopefully you can kind of see that the NH3 concentration would go down. And if the NH3 concentration goes down, think about your equilibrium again. So if NH3 goes down, that would mean that your fraction is now too small. So the reaction needs to proceed in a way that raises that fraction back up. So it's going to need to produce more NH3 to offset the loss of NH3. So in this scenario, if we added an acid or lowered the pH, the reaction would then shift to the right to try and produce more NH3. You can go through this whole process of thinking about KEQ and how the disruption changes the value of that fraction. Or you can pretty much just think about what happened, what was my disruption, and what direction does my reaction need to proceed to do the opposite thing that disruption did. That second route is what you should be doing on the test because it's way faster, but you do need to understand this justification so that way if something new comes up on the test, you can think your way through it. So far, we've only talked about equilibrium in terms of the concentrations of the reactants and products, and now we're going to talk about what you do whenever they're talking about the partial pressures of gases that are involved in a reaction. First, remember from one of the previous videos about other gas laws, we said that the partial pressure of a gas is directly proportional to the number of moles of that gas. And so what that allows you to do is basically equate the partial pressure of a gas to the concentration of a gas. So whenever gases are involved and the partial pressures are given to you, you can use the partial pressures instead of concentration and plug them into this equilibrium constant, Kp, and Kp is equal to products over reactants raised to the coefficient, but it's using the partial pressures instead of the concentrations of those gases. And it's set up pretty much the exact same way where we have the partial pressures of the products on top and they are raised to the power of their coefficients over the partial pressures of the reactants raised to the power of their coefficients. You want to think about these problems the exact same way that we've been thinking about it before, where at equilibrium, this fraction is equal to the value of Kp, and that Kp is an unchanging value. That's a constant that would only change with temperature. There's an additional way that they can test you on this concept, and that is whenever they tell you that the total pressure of a system has changed. And we're going to use this reaction down here to go over an example that is just like that. On the right side, we're asked what direction will the reaction proceed if the volume is decreased by 50%. The very first thing you want to think about is that if volume decreases by 50%, then that means the pressure has gone up, and it has gone up by exactly 2 times. So we are dealing with double the pressure. Anytime the pressure goes up in a system, the reaction is going to proceed in the direction that lowers that pressure. And the way it does that is by proceeding in the direction that creates less moles of gas. So look at your balanced reaction to be able to tell this, and look at which side has less moles of gas. On the left side, we have 1 mole of nitrogen gas, 3 moles of hydrogen gas. So there are 4 moles of gas on the left side. And then on the right side, we only have 2 moles of NH3 gas. So there are 2 moles on the right side. So based off of this logic, if the pressure is increased, the reaction is going to proceed to the right because that will help to lower the pressure because it's creating less moles of gas. You can also look at this mathematically if you're curious about that. You don't need to, so if you don't want to worry about it, you're totally fine just thinking about it the way that we've gone over, and you can skip this next part of the video. But to think about it mathematically, let's first set up our Kp equation, just like what we have on the left, where Kp is equal to the pressure of the products over the reactants. Since we weren't given any values, let's just make up some variables here. So we're going to say that Kp is equal to x squared over y times z raised to the third. So we just plugged in some variables to represent the partial pressures of our gases. Now we want to look at that fraction after the pressure has doubled. So if the pressure has doubled, instead of x squared, we now have 2x, because remember x represented the partial pressure, which is now doubled. So it's 2x over 2y times 2z, and then raise everything to those powers. So it'd be 2x squared, and then the 2z would get cubed. Now you distribute your squared and your cubed, and you'd end up with 4x on top over 2y times 8z. And the way that you would distribute the cubed and the squared, it would have to be applied to both the number and to the variable. So it's not only 4x, it's actually 4x squared and 8z cubed. So after you've done that, now look at by what factor have we increased the top and bottom of your fraction. So on the top, we went from x squared when it's at equilibrium, so we have 1x squared over here. Now we have 4x squared. And then look at the bottom. So the y went from just 1y to 2y, but the z has gone from 1z cubed all the way up to 8z cubed. So the bottom of your fraction, the one that had more moles of gas because that represents the reactants, that has been increased by a greater magnitude, because the more moles you have, the larger those exponents are in the equilibrium reaction. So whenever you increase the pressure, that part of your equilibrium equation gets amplified that much more than the parts that have less moles of gas. In this last part, we will talk about how you apply the ideas of equilibrium to situations where they're talking about heat in the reaction. We haven't gone over exothermic or endothermic yet in this video series, so that'll get covered later, but for right now, all you need to know is that in an exothermic reaction, heat is produced, and in an endothermic reaction, heat is required to get the reaction going and heat is absorbed. So the way that you can think about this is that for exothermic, heat is a product, and for endothermic, heat is a reactant. And now all you have to do is apply this to situations where they are saying that the temperature is changing. If they say that the temperature is going up, then all you need to do is think about that as an addition of heat. So if temperature goes up, that's basically adding heat. And then if temperature goes down, that is basically subtracting heat. And then all you need to do is think about heat as that product or reactant, and then apply either the addition or subtraction of heat, and then go through your normal thought process about equilibrium. So let's just say for exothermic, if we added heat, now we have too much of our product and the reaction needs to go in the direction that offsets that change, so then the reaction would go to the left. And then the opposite would be true. If we said that we subtracted heat, then that means that we're losing some products, so the reaction will offset that by going to the right. And then you just apply that same exact logic to endothermic, so we'll just do one real quick. If we added heat to an endothermic reaction, that would mean we're basically adding products, and the reaction would proceed to the right to try and offset that change.